Hello again, ladies and gentlemen. This will be a talk on the normal distribution and z-scores, a very, very, very important concept in biostatistics. This is one of those things that not only will it come up on the USMLE, but you will use this every day if you read medical journals. So very, very important. Now, hopefully you have watched my original talk on biostatistics, the first one where I go over the rudimentaries, what's mean, what's median, what's mode, what's variance, standard distribution, all of those things, very, very important, because right now in this talk we are going to build on that. So if you haven't watched that video or you don't understand what those things are, you'll want to go back and watch that video before you start on this one, because this one's building on that. If you haven't had the opportunity yet, please consider subscribing to my Patreon page at www.patreon.com/pwbmd. You can click the link below in the description of the video or on the I button on the upper right-hand corner, and it should link you up. If you consider chipping in $1 a month, a little bit goes a long way to help keep these videos free. If you subscribe, you'll have access to some of my premium videos in which I go over case reviews and how to formulate differential diagnosis and treatment plan, things that are very, very important for clinical practice and for step 3 of the USMLE. Thank you very much in advance for your consideration. So we're going to talk about the normal distribution, really what it is, why we use it, and the normal curve, which is really just a graphical representation of the normal distribution. And then we'll talk about z-scores and certain applications of those z-scores, and how this really comes into play when we're talking about medical statistics, when we're talking about when we read these journals and we see these different things, what do they mean? And what do they tell us about statistical significance and stuff like that? The USMLE loves to test this stuff because, like I said, it comes up in medical journals. You need to read medical journals to function as a healthcare practitioner and stay up to date. So you need to know this stuff. So the normal distribution is also known as the Gaussian distribution. It's a continuous probability distribution with a symmetrical distribution, and it has an identical arithmetic mean, meaning the average value, the mode, meaning the most frequent value, and the median, meaning the middle value. It's all the same. Now, this is different from some other distributions. This is really a formal definition. There's other distributions that come up in statistics, the binomial distribution, Poisson distribution. You do not need to know those at all. So if you studied those in your medical statistics class, you don't need to know those for USMLE. The only one you need to know is the normal distribution. So they keep it kind of simple for you. The shape of the normal curve, this is the one we're used to. This is the standard normal curve. But there's different shapes of normal curves, and that shape is determined by two important variables, the mean and the standard deviation. The mean may be given to you as mu. That's the population mean. So the mean of the population at large. Or it could be given as x bar, an x with a little bar over the top. That's your sample mean. So if you take a group from the population and test them instead of testing the population at large, it gives you a sample of the population. So you have a population mean and a sample mean. Population mean is mu, and the sample mean is x bar. Then you have standard deviation, as you know what that is. So there's a population standard deviation, which is sigma, or there's a sample standard deviation, which is denoted as S. We're primarily dealing with samples. So we'll see x bar and S come up. But you may see in different formulas, you may see mu or sigma come up, and it's really just standing for the same thing. You're just dealing at the population level instead of the sample level. All the formulas are the same though. So a standard or standardized normal distribution is one where the mean is 0 and the standard deviation is 1. And we can take any kind of normal distribution and standardize it. And we standardize it with a particular formula, and we'll see how we do that on the next slide. So this is the actual formula for the probability distribution. You do not need to know this formula at all. So I just put it here for completion's sake, but please do not memorize that formula. It would be a waste of brain space. So this is the standard normal distribution. And what you can see here is an important concept, and that is the z-score. And we're going to talk about that on the next slide. But what that score tells us is that anything below that score, when you can take any number, so let's say you're talking about weight or height, you can take that as long as you know the standard deviation and the mean. You can take that and convert it to a z-score. And what you can do from that is you can determine what percent of the sample or the population is below that level and what percent is above that level. And that's useful. That's how we determine like percentiles. Like when you took the MCAT, you got a percentile back. That was done by standardizing the scores that everybody got and then plotting you somewhere on that normal curve and then determine the percentile. So you can see an important value on the standard normal distribution, a z-score of 0. So a z-score of 0, 50% will be below it and 50% will be above it. A z-score of 0.5, 69.1% will be below it, and the difference, I guess that would be 30.9%, would be above it. And you can find out all of these probabilities of falling below it or above it based on the z-score with a table. So you don't need to memorize that. If you're asked anything like this on the USMLE, they will give you a table. Even upper level statistics courses give you a table. You never need to memorize these. So the z-score represents how many standard deviations a value is from the mean. So if you have a positive z-score, it means that your value that gave you that z-score is above the mean. And so if it's negative, it means that it's a value below the mean. So if you say, let's say you take your height in inches or centimeters, and you find out what the z-score of your height is. If it were a positive z-score, then it means you're taller than average. If it's a negative z-score, it means you're shorter than average. So that's all that means. The z-score is just a standard representation of our variable that converts it into a form that can be useful to us for probability. So you can determine the probability that a value will fall beneath the z-score by using a table. And this is an interesting table. Now, there's one thing that I don't like about this table, but basically what you do is you find your z, and let's say it starts with a 0, then here's your 0, and then your first decimal point. So a z-score of 0.2 means that 57.93% of your values will fall beneath that z-score. And obviously, if it's 0, 0.0, it means 50% will fall below, which we know because it's a symmetric curve. The reason I don't like this is that it's giving you values in percentages rather than in decimal form, and usually we'll use it in decimal form, especially when we get to talk about one of the applications of the z-score. We need to use the decimal. So I'm not a big fan of this, but I have a couple other pictures of tables. There's all sorts of tables. You can find them online. Like I said, you don't need to memorize any of these values. Usually the distribution is not standardized. So normally, if we have a standard curve, then the z-score will equal the value of x. But normally that's not the case, because when we have, for instance, a height curve, like let's say we have a standardized or a normal curve, and we're plotting height. Well, obviously the average height is not going to be 0 inches. It's going to be, a certain number of inches, but it's not going to be 0. We can take that curve that gives us height, we can take the standard deviation of it, and we can take the mean of that curve, which we know, and then we can take that to find the z-score. So here's how we do that. To find the z-score of a non-standardized curve, what you do is you take your value that you're trying to find the z-score of, you subtract the mean, which you should know, and then you divide by the standard deviation, and that will give you a z-score. Now, as you can see, if you had a standardized curve where the mean is 0 and the standard deviation is 1, well, then your z-score is going to equal x, because x bar is 0 and standard deviation is 1, so you just have your z-score equaling x. So this is how you take a value and you find the z-score of it. And what you need to know is the mean and the standard deviation, and then you can find your z-score. And then when you take that z-score, you know what percentile you're in or what percentage of the sample or the population is beneath that value. So if you get a z-score of 1.0, you know that 84.13% of values are below that particular value of x, or a probability of 0.8413. Okay, so that's the z-score. So these are the tables that you can find, and typically when they give you the probability for the z-score, it's going to be the probability of being below that score. Some more advanced tables will give you different probabilities. Some might give you the probability to the right. That's useful if you want to find what percentage are going to be above a score, obviously. But for our purposes, you just need to know how to determine the probability beneath the score or the z-score. You can very easily find the probability of being above the z-score. You just take the probability of being below and you take 1 minus that probability. So obviously, if let's say this is 80% of values right here, well then you know that if 80% of values fall beneath the z-score, then you know that 20% of them will fall above the z-score. It's kind of like percentiles, right? So if you take your MCAT and you're in the 90th percentile, then it means 90% of scores were below you and 10% were above you. And it tells you that down here. So this is just another example. I like this better. So here you have a z-score. This is just showing that the third decimal is 0. But say you want a z-score of 1.20, then you can find the probability of being to the left of that. Being below it is 0.8849 or 88.49%. So let's try an example here, and you need to know that formula that I gave you. So if you don't remember that, go back and look. So suppose tree diameters of a certain species, I know this is botany and not biology, but whatever. Tree diameters of a certain species of tree from some defined forest area are assumed to be normally distributed with a mean of 8 inches and a standard deviation of 2 inches. What's the probability of a tree having a diameter greater than 12 inches? So try to conceptualize this. What are we asking here? I'll let you pause and then I'm going to walk you through it. So what we want to know is the probability of falling to what side of, so we're going to find a z-score here. Do we want to know the probability to the left or below the z-score or above? So what we want to do is we want to find actually here the probability of falling above the z-score because we want to be greater than 12 inches. So your first step, whenever you're given a question like this, is to find the z-score. That's always your first step. So find the z-score for 12 inches. That will give you the probability of falling below that. And if you know the probability of falling below that value, then you can easily find the probability of falling above that value. It's just 1 minus the probability of falling below the value. So let's find our first of all, is this data standardized? So obviously no. If it were standardized, the mean would be 0 and the standard deviation would be 1. So this is not standardized. So our next step is to standardize the data and obtain the z-score. We're just going to obtain the z-score through that standardization formula that I gave you. So that's this formula here. So x is our variable. That's going to be 12 inches. 8 is the mean, and 2 is the standard deviation. So 12 minus 8 over 2 is 4 over 2 is 2. So that is our z-score. It's as simple as that. As long as you know the mean and the standard deviation, you should be able to find your z-score very easily. So 2 is your z-score, and then all you need to do is look at your table. So here's your table. And you want to find the probability that a value will fall above 2 because we want to know what's the probability of it being greater than 12 inches. If we wanted to find the probability of it being smaller than 12 inches, well, then you look below that z-score. So really, this z-score is just converting this value in inches, this variable x, into a score that's standardized that we can use to find probability. So what's the probability that the value will fall above z equals 2 or x equals 12 inches? And all you need to do is look here, 2.0, 97.72%. Now that's the probability of falling below it. The probability of falling above it is going to be 1 minus that probability. And so that's going to be 1 minus, and I put it in decimal form here, 0.9772, and that's going to be 0.0228 or 2.28%. So you may see this if you read books on statistics or maybe some of your review material. You may see it described as phi of your z-score. So phi, in this case, phi of 2. Phi of 2 would be 0.9772. Or you may see it denoted as probability of z less than 2, and then that would be this value here. Remember that your z tables are typically going to give you the probability that it falls below that z value. Okay? If you have any questions on this, write me a note below. Okay, so let's apply some of this stuff, particularly some of this stuff that we learned about in the previous video. And this is the standard error of the mean. So the standard error of the mean is just an estimate of the quality of the sample that you took and how good that sample and that estimate is at making an estimate for the larger population. So whenever you do take a sample, let's say you want to figure out what the average blood pressure is for a population in a city, and you take 50 people from that city. You can't take an entire city of 100,000 people and test all their blood pressures. That wouldn't be realistic. But what you can do is you can test 50 people, and then you can make an inference as to what the average blood pressure in that city might be, or maybe a population given a certain race or something like that. So what you do is, to find the standard error, is you take your sample, you plot it, you find your standard deviation, which we already talked about how you do. It's just the square root of the variance. You find your standard deviation, and then you divide it by the square root of the sample size. So our sample size is denoted as n. That's just the number of people that you took measurements on. So the number of measurements. So it's standard deviation divided by the square root of the sample size. And that will give you your standard error of the mean. And that tells you how good the quality of that sample is. And really, all it's telling you is that it's better to have a lower standard deviation, and it's better to have a higher sample size. So what would increase the standard error? The standard error is just, it really is telling you how accurate your value is in all likelihood. So a larger standard error would mean that there's a larger chance of error in the estimate of the mean when we're estimating the mean, right? So what would cause that to go up? Well, if S went up, so if you had a larger variance among the population, that would tell you, it's really hard to get an average when everybody's kind of all over the place. So a higher standard deviation or variance, remember the two are inextricably linked together because one's just the square root of the other, or a lower sample size. So obviously if you took a sample of 3 people out of a population of 1 million, and you took the average of their blood pressures and said this must be the average for the entire population, well, probably not, because you only sampled 3 people. Or let's say, this is kind of getting more towards binomial stuff, but let's say you took a poll of who the person is going to vote for in the next presidential election out of 2 choices, and you took 3 people. Can you say that is going to accurately predict who's going to win the presidential election? Absolutely not. You only have 3 people. You're going to have a massive standard error. And this kind of gets into the margin of error that you see in polling, which tells you kind of how accurate this data is. If you have a larger standard error or margin of error, you're going to have, you can't really take that as, you have to take that with a grain of salt, because it's going to be a wider range that the true value could actually fall in. Okay, this gets us to the bread and butter of our talk here, and that is the confidence interval. So the confidence interval of the mean, and that's the full name, the confidence interval of the mean, is an interval within which we can be a certain percentage confident that the value falls within it. So there's different confidence intervals. There's like a 90% confidence interval, a 95% confidence interval, a 99% confidence interval. There's different confidence intervals that we can use. The one that we most commonly use is the 95% confidence interval, and you've probably seen this in the literature. So 95% confidence interval, and what that tells you is the interval between the 2.5th percentile and the 97.5th percentile, 97.5th percentile. So what that means is that 95% of the possible values will fall within this interval. 2.5 will fall below and 2.5 will fall above. But this interval will include 95% of all the possible values. So to obtain the to obtain any confidence interval, what you do is you take your mean and then you add or subtract z, which is going to depend on what confidence interval you want, times the standard error, which is s over the square root of n. So when we do the 95% confidence interval, which is really going to be the only one I think that'll come up on the test, you're going to use z equals 1.96, or you can round that to 2 for calculation purposes. So what that tells us here is if you go 2 standard deviations or 1.96 standard deviations above and 1.96 standard deviations below, that total beneath the curve should include 95% of all your values. And we need to center it around the mean because we want to know what the confidence interval is of that mean. So here's a closer look here. So here's 2 standard deviations below, 2 above. You get about 95%. So that's the only z value you should remember, is the 1.96 or 2, which is needed to give you your 95% confidence interval. And you're taking both negative 1.96 and 1.96. So that's just included here, plus or minus z times the standard error. So we use this confidence interval when we want to determine whether or not the sample we took is representative of the mean. So here you have a variety of different samples that were taken. And all of these samples, even though the mean may be a little different than what we take here as the population mean, the true mean, even though the mean of each of these samples may be a little bit below or a little bit above, the 95% confidence interval includes the population mean. So there's a 95% chance that within our 95% confidence interval, it's likely that population mean, or it's true that population mean falls within that 95% confidence interval. And so we can say that there's no statistical significant difference between our sample mean and the population mean. So if the sample mean and the population mean are within the same 95% confidence interval, then it tells you there's no statistically significant difference. The only one here where the population mean is not included within the 95% confidence interval of the sample mean is this value right here. And so for this sample group, we can say that there's a statistically significant difference between the sample mean and the population mean. So something happened here where we took a sample of a group that was predisposed to be different from the population at large. All right. So here's another example of how it could be given to you. So you don't just look at the mean. Okay, you have to look, you can't just look at this value right here and say, well, this group was statistically significantly lighter, because this is weight, than the population at large. No, what it's telling you is just by chance you happen to get some people that were lighter. It's not telling you that just having this mean down here from the sample doesn't mean anything if the 95% confidence interval includes the population mean. So this is the only one that's statistically significant here because the 95% confidence interval does not include the mean. And I'm going to give you a really good example of this, how you really use this in real life in a little bit. Okay, so this is our big example here, and this is just to put everything together that we've used. So suppose 10 children in a kindergarten class are taken randomly, and their heights are measured. Their heights in inches are 46, 43, 40, 42, 39, 44, 41, 43, 45, and 40. What is the mean, the variance, the standard deviation, the standard error of the mean, and the 95% confidence interval of that mean? So you'll want to pause it here, and this is just good practice to go through and try each of these. You should know how to do each of these based on the formulas. These are all formulas you'll need to know. And you can go back and look at these formulas if you want, but you'll want to know how to do this. And I'm going to pause it here. Okay, so what is the mean? So the mean is pretty easy. It's just the average. And it's just, that's your x bar, because this is a sample mean. and it's just the sum of all these values divided by the total number of values that there are, and that's going to be 42.3. Okay, so that was easy enough. What about variance? Do you remember how to do variance? So this will take you a little bit longer. And I don't care if you actually get the value. All I care about is that you know how to do it. Okay, so the variance is the sum of the difference of each of these values from the mean squared. So you take, let's say, 46 for your first value minus the average, the mean. So 46 minus 42.3 is 3.7, and then you square that, and then you add that to the next one. So 43 minus 42.3 is 0.7, and you square that, and then you do that so on and so forth all the way to the end. And you take all those values and you add them together. So 3.7 squared plus 0.7 squared plus and so forth all the way to the last one, which is 40 minus 42.3 is negative 2.3. And you take that squared and you sum all of these up and you divide by n minus 1. So when you're doing this for a sample, you have to do n minus 1. And so that's going to be 10 minus 1. I don't think you'll ever be asked to do something this long on the test. It just takes too much time. But you should know how it's done. And that's 5.34. So that is your variance. Now what about standard deviation? That shouldn't take you very long. What's standard deviation? It's the square root of the variance. So square root of 5.34 is 2.31. Standard deviation is important because that fits into all these formulas that we've been using. So now something we talked about today, the standard error of the mean. How do we determine that? The standard error of the mean is the standard deviation divided by the square root of the sample. So that's going to be 2.31 divided by the square root of 10, which is 0.73. So now you should be able to do your 95% confidence interval. Your 95% confidence interval is your mean plus or minus the standard error, your z-score times your standard error. So your z-score here is going to be particular for your 95% confidence interval. If you were doing a 90% confidence interval, you'd use a different z-score. But 95% confidence interval is what everyone uses all the time. So that's going to be the one if they give you one on the USMLE. So remember that your z-score for the 95% confidence interval is 2 or 1.98. You can round to 2. And then, so your mean is 42.3. Your z-score is 1.98. And your standard error is 0.73. And you will then take this value, which is 1.45, you'll add it to 42.3 and then subtract it away from 42.3. And that gives you two values, your lower value and your upper value, and that range is your 95% confidence interval. So 40.85 to 43.75. So what does this tell you? So at first glance, you might say, well, the mean is 42.3, so this group of kindergartners is not representative of the general population. And if that were the case, you might think, well, are these children being exposed to something that's causing them to grow faster? What's going on? Well, when you take that, you take that mean, you might think that. But when you look into the data and you find your standard error and then you find a 95% confidence interval, what this is telling you is based on the error that we might get that we're only testing 10 kids and that they have this variance, is there a 95% chance that the true mean of the population, 41 inches, may fall within that range? And what that tells you then, if that value falls within the 95% confidence interval, what that tells you is that there's no statistically significant difference. So what we do find is that 41 inches does fall within the 95% confidence interval. So this group of children, even though on average they are taller than the general population of kindergartners, that they are representative of the general population. Okay. Now let's say that the average height of kindergartners was 40 inches. Well, then this would definitely be statistically significant difference because that falls outside of the 95% confidence interval. And we would expect that confidence interval to narrow if we have a larger sample size. So if your sample size gets bigger, this standard error gets smaller. And that means that this value goes down, and that's going to reduce the size of your 95% confidence interval. All right. So how do we apply these confidence intervals? This is a good way to apply it to medical literature. So suppose a study is performed on 3 different pills thought to reduce the risk of stomach ulcers. Relative risk, which is the risk of the illness on a certain intervention, in this case a pill, divided by the risk of illness on placebo or on no intervention. And this is obtained along with a 95% confidence interval. How do you interpret this data, and which pill is the most promising? So here's pill A, relative risk of 0.8. So the people that were on this pill had a 0.8. The ratio was 0.8. So it means that people on placebo were more likely to get it than the people on the pill. So the pill appears to be protective. And then the confidence interval is 0.62 to 0.91. Pill B, relative risk of 0.6. So again, looks like on face value, looks like it reduces the risk. 95% confidence interval is 0.5 to 1.10. And pill C, relative risk of 1.2, and 95% confidence interval of 1.04 to 1.33. So what does this mean? Which of these are statistically significant? Which of these pills is the most promising? Which of these pills, if you had to choose one to give to someone with a stomach ulcer and they were all FDA approved, which would you choose? So the meaning here is that pill A and pill C are both statistically significant. Why are they statistically significant? Well, we have something that we haven't introduced yet called a null value. And the null value is a value that tells you that there's really no effect. In this case, there's no effect. And what that would be is the relative risk of 1.0. So 1.0 means there's no effect. You might as well give a placebo to everybody because there's no effect of the pill. If so, what you're looking at then is that 95% confidence interval. Does it include that null value of 1? If it does not, then it's statistically significant. And the null value is not always 1, but in this case it is because we're talking about relative risk. So if that confidence interval does not include the null value, then the results from that pill were statistically significant. So look here. So 0.8, the confidence interval is 0.62 to 0.91. What that tells you is that 95% of the times, if you were to repeat this study 95%, or if you were to repeat this study over and over and over again, 95% of the time, you'd have a value falling within this range. So that tells you that it's statistically significant because it does not include 1. So this is a statistically significant reduced risk because all of the values are beneath 1 in that confidence interval. Well, pill B, if you look at the face of it, you'd say, well, look, our results showed a relative risk of 0.6. That's the lowest risk. This appears to be the most effective. Well, something happened in this study. We had either too small of a sample size or we had too much variance. And look at our confidence interval. It's huge, and it includes our null value of 1. So what this tells us is that it's not statistically significant due to the variance or the small number of people being studied. It's not statistically significant. So we can't say whether or not there's an effect. There may be an effect if we study enough people. This confidence interval may shrink below 1, and then we could say that it is statistically significant reduced risk. But at this point, it's not statistically significant. And then pill C, we see a relative risk of 1.2, which would mean that it increases the risk. But we got to look at the confidence interval, and we can see that the confidence interval does not include 1. So 1.04 to 1.33, that is statistically significant, and that's an increased risk. This is more than likely how you're going to see confidence intervals provided to you on the USMLE. It's going to be in the context of relative risk, because this is just the easiest way they can put it to you. And typically, statistic questions on the USMLE are not going to be very difficult. They're going to be relatively straightforward. So as I said, for a result to be statistically significant, it cannot include the null value. So just to recap, remember your z-score is the number of standard deviations away from the mean. That's just your value that you're trying to find the z-score on minus the mean divided by the standard deviation. This phi of your z-score is the probability of a random variable falling beneath the z value, and you use your tables to find that. The standard error of the mean is a measurement of the quality of a sample in determining the true mean of the population. That's going to be your standard deviation divided by the square root of your sample size. And then the confidence interval, which is right here, this formula. And that is the interval within which we can be certain that a certain percentage, usually 95%, will fall within that interval. So like I said, typically we use 95%. You'll want to remember that for the 95% confidence interval, we're using a z-value of 1.98 or 2. And that's all I have for you. I will see you next time.